Alright, ladies and gentlemen, in this video we're going to be looking at an example of how to solve a problem involving friction on an inclined plane. I'm using question number 36 from page 133, and this is from somewhere near the end of chapter 5 in our physics textbook. So the deal with this question, the situation is we have a child named Fernando, and Fernando is sliding down banister of a stairway. Okay, so you can imagine kind of simple stairway, and Fernando is sliding down. Oh, by the way, this right here, the railing, is the banister. We're given a little bit of information about the situation. Fernando, the name of the child sliding down, has a mass of 43 kilograms, 43.0 kilograms. And we're told that the angle of the banister is 35.0 degrees. All right, so this particular question is asking for what is the normal force between Fernando and the banister. I'm also going to look at a couple other questions. I'm going to ask what if Fernando slides at a constant velocity. So if velocity is constant, then I want to know what is the force of kinetic friction between Fernando and the banister. What is the force of kinetic friction acting on Fernando as he slides? I also want to ask, what is the coefficient of kinetic friction for this situation? So here's the original question, the normal force. Then we want to know, well, if he slides at a constant velocity, what is the friction force acting on him while he slides? And finally, what is the coefficient of kinetic friction between Fernando and the banister? So one of the first things we want to do is try to set up a sketch of the, we have a sketch of the situation. We want to set up a free body diagram, right? And as is almost always going to be the case, we want to have the angle of the ramp represented in the free body diagram by tilting the axes, the coordinate system. So I have my y-axis, my x-axis, and so there are some forces acting on Fernando. And if I switch colors, this might be easier to see. We know that Fernando has a certain amount of weight, and weight is always acting straight down. Weight is just the force of gravity. Well, we also know that weight is mg. So at this point, I know his mass, and I could calculate his weight. That will probably have to happen. There's also, because of Fernando's contact with the banister, there are a couple other forces. We know that there's going to be a normal force. In fact, that's the first question we're going to try to answer. There's going to be this normal force here, which will always be perpendicular to that surface. Perpendicular is going to be straight up. So we have this. I'm sorry, I shouldn't say straight up. Perpendicular to the surface will be parallel to the vertical y-axis here. That's our normal force. Okay. Now, as he slides down, we're going to have. I'll use a different color here. I'll go back to. Well, velocity in the downward direction, down the banister, I should say. Got to be careful how you phrase these things. That's down. This is sort of down the banister along that surface. And as he slides, he's going to have friction opposing his motion. So friction will work up this way. Don't quite know at this point how long to draw these arrows relative to each other. It's kind of a guess at this stage, but this is the force of kinetic friction right there. Okay, So there is nothing else touching Fernando that's of importance here. We have gravity pulling down. We have two forces created by Fernando's contact and motion right here along this surface. First step, first goal, I want to answer this. Well, I want to find out the amount of the normal force. So if I were to look at this, just, well, I can even just put it right here on the main free body diagram. What I know I can do is, looking at this, well, that doesn't have any x component, it's all in the y direction. This one doesn't have any y component, it's all in the x direction. So those two don't have to be broken up into separate components, but this one does, and that'll be useful. So there's just a quick visual technique. I can just kind of say, well, little line there and little line here, and I'm going to make basically a rectangle like that. And so those extra lines I drew are just sort of reference lines, but they tell me something pretty important. This force, this weight right here, some of it is going to be in the y direction along the y-axis, and it turns out it's going to be just this much. So now this doesn't give me the answer to how much it is, but it tells me visually. And the same thing here. I kind of messed up on being parallel, not exact. Okay, but it's close enough. So right here, some of this weight is in the x direction, and it will be that much. So here's the deal. That is force of gravity in the y direction. And this is the force of gravity in the x direction. And that's important, because what I know about Fernando's situation is that he will not be accelerating in the y direction. In fact, he's not even moving in the y direction. So everything in the y direction must balance out. Fernando is moving in the x direction, but he's not accelerating in the x direction, and that's kind of important. Our situation called for constant velocity. So no acceleration. And if there's no acceleration, then again, even though he's moving, the forces must still balance out in the x direction. So what this is telling me is I have a situation of equilibrium. And when there's equilibrium, I know that the sum of the forces in the x direction will equal 0, and also sum of forces in the y direction will equal 0. This does not mean there's no motion, it means there's no acceleration. The motion is not changing. So it's true there's no motion vertically, but it's going to remain no motion vertically. There is motion vertically in the y direction. There is motion in the x direction, but it will remain constant motion. It will not change. Okay. Well, my first goal is that normal force. So I know that it must be balanced by this other force in the y direction, that guy. So forces in the y direction must add up to 0. Well, that just tells me that the normal force must be equal to the force of gravity in the y direction. Can I find that guy? Because if I can, well, then I can know the normal force. Well, right here, you really want to be able to see that this weight here and this component of the weight, and really this imaginary line, which is equal to that guy, they make up a right triangle. You've got a hypotenuse there, which is just the weight. You've got a little side here and a longer side there. And there's your right angle. The right angle is right here. And there's an angle here, and of course there's an angle here. But here's the deal. When you're trying to identify where the angle of the banister is located, this 35-degree angle, where does it show up here in the diagram? One way to look at this, and this is going to get a little complicated in the main diagram. Sometimes it's useful to redraw things, but I'm just going to add it in right here. This line represents horizontal. So we know that this is our angle theta. This is the 35-degree angle. We matched the x-axis with the angle of the banister, the angle of the surface. And that's our technique for setting these things up. But how does that relate to this triangle? Well, I didn't quite get it down here to the ends, but it doesn't matter. Here I have this right angle between the two axes. And if I look at this tiny triangle right here, I have a right angle here. And so I've got a situation of similar triangles. Now, this large triangle has this smaller angle theta over here. But the smaller triangle right here, you would see theta right there in those two similar triangles. So what that tells me is for this triangle here that I'm dealing with, when I'm looking at this weight and the two components of it, by the way, this is FG in the y direction, this is FG in the x direction. I know where theta is located. It's up here in this corner of the triangle. Now I'm looking for the y component of weight, because once I know that, I can know the normal force. So I want to solve for that guy. Well, that guy happens to be adjacent to the angle. So that tells me I want to use the cosine function. Cosine of an angle is equal to adjacent, which is FG in the y direction, divided by hypotenuse, which is FG. So if I'm looking for the y component, it is simply FG cosine theta. I know that the weight, Fg, is just mass times acceleration due to gravity. And I know both of those numbers. And I multiply by cosine of theta, and I know theta. So at this point, I'm good to go. I can find the y component, and therefore I can find the normal force. So the mass of Fernando. He had a mass of 43 kilograms. G is 9.8. And the cosine of the angle is 35 degrees. Now squeeze it in here at the bottom. And I get an answer of 345 newtons. So that y component is 345 newtons, and that tells me the normal force. I now have the first answer. It's right there. So you can see what's going on. There's use of geometry here. There's use of knowledge of equilibrium going on and forces that are balanced. And really this kind of comes from Newton's second law as well, but that's Newton's second law is just F equals ma essentially. But what we mean by this is, well, we have zero acceleration, so we must have zero net force. And zero net force means when you add all the forces together, you get zero. So that's how Newton's second law is used here as well. Well, now there's a couple other questions I need to try to answer. Looking at this original sheet, if the velocity is constant, what is the friction force? Well, okay, so I'm going to come back here. I don't have room to solve for it here, but I can look at it. Now I want to find that kinetic friction force, right? Well, sum of forces in the x direction must equal zero. This friction force in the negative x direction must be balanced by this component of weight in the positive x direction. I didn't draw them equally, but I didn't know how long to draw this arrow, so I can simply work this out. I can do the same thing I did here with those x forces. Maybe I do have room here. Possibly. No, don't want to squeeze it in. Don't want it to get sloppy for you. Sorry. I can do better than that. So what we're looking at is simply the kinetic friction force. I know it has to be equal to the weight in the x direction. Those two have to balance. If I were to add them, I have to get zero, so it should work out. Now, how do I find that component of weight? Well, it's going to be very similar to what I did here, except now I'm looking for the x component. The x component happens to be opposite of angle theta, and it's way across the triangle over here. And so I won't use cosine, I will use sine. And that relationship for a right triangle is going to equal the opposite side, which is weight in the x direction, divided by the hypotenuse, which is just weight. So I'm looking for weight in the x direction, or the x component of weight. And so it's just Fg sine theta. And I know Fg, it's just mg once again, times sine of theta. And so I know all of those values. Again, I use 43 kilograms. I multiply by 9.8. You always have to remember, and this is kind of a common mistake, that 43 kilograms is not the child's weight. It's not Fernando's weight. It's his mass. And to find his weight, we need to multiply by the acceleration due to gravity, which is the 9.8. So, back to this. I know the angle is 35 degrees. Okay, so when I multiply, handy dandy calculator, $240 rounding off 242 newtons. And so I have the answer. Got the box a little sloppy, sorry. So that is the amount of friction, 242 newtons, acting on Fernando as he slides down. And it's acting to oppose his motion. The final question that I'm asked about this situation is, what is the coefficient of kinetic friction here? This is kind of a simple situation. But what you'll see, though, is we get to a point where we are coming to the relationship between the amount of friction and some force, something right here. And this is the work you've done recently on your lab. And remember, we can't use weight here anymore. We learned in that lab experience that, well, if you change the angle of the surface, the weight does not change. However, the friction does. So something else has to go here. And it turns out it's just normal force. Changing the angle of the surface does change the normal force and also the amount of friction. That's the connection. That's the real form of the equation that we want to use all the time. It turns out that when the surface is horizontal, the normal force equals the weight. And that's kind of cool, but that's just a special case. This is what we want to do. However, it's our goal to find the coefficient. So I'm just going to rearrange this equation. The coefficient of kinetic friction is going to be equal to the force of kinetic friction divided by the normal force. And so I know the amount of kinetic friction force. I just found that up here, 242 newtons. And I know the normal force. I found that here. That was 345 newtons. So, real simple calculation. 2 divided by 0.70. If you're crazy about sig figs, you might want to go to one more sig fig. Really doesn't matter much. But there you go. That is the final answer. Now, that is what you call the coefficient of kinetic friction. I kind of messed up on that symbol, didn't I? Be a little careful. That's a little better. So, no units here. Well, when you do this, those units cancel out, and there's nothing left. That's why it's called a coefficient. The coefficient is just a number, no units that go with it. So there you go. This is typical of how you deal with problems like this. You're given a situation on an inclined surface, on an angled surface, right? And you might be asked a few questions about it. The normal force, the amount of friction force, the coefficient of friction in that situation. You have to be given a little bit of initial information. We were given mass and the angle, and it turns out that was enough. We worked through creating a free body diagram, and we recognized we had a situation of equilibrium. The free body diagram helped us determine the x and y components of weight, and those x and y components allowed us to see how the forces in the y direction must be balanced and also the forces in the x direction must be balanced. And a little bit of geometry work to get us those components, and then using that to get us the answers. Now, this was a situation of equilibrium, right? Where these two arrows really need to be drawn the same length. So I'm going to try not to get too sloppy here, but if I keep that green arrow, then really the red arrow should just be about this long, right? And got to get rid of that so that they balance. It is possible that the forces do not balance. But if they do not balance, then you simply have an acceleration. It could be speeding up as it slides down, or it could be slowing down as it slides down. Either one is a possibility, but they weren't involved in this problem. Thanks for watching. I will catch you next time.